Next, we're going to see how to prove a statement of the form P if and only if Q. So let's recall what if and only if means. So recall that if and only if, P if and only if Q is logically equivalent to, meaning it has the meaning of if P then Q and if Q then P. So if I want to prove a statement of the form P if and only if Q, what I have to do is prove that if P then Q and also prove that if Q then P. So here's an outline for an if only if proof. So we have a proposition saying P if and only if Q. Well, this is obviously just a general form of the proposition. So we're going to have two parts of the proof. We're going to have to prove the forward direction and the backwards direction, meaning we're going to have to prove that it goes from P to Q, that if P then Q, and then we're going to have to prove that if Q then P. So we'll call this the forward direction, that's the first one, and then the backward direction. So for the forward direction, we prove if P then Q using any method. We have three different methods already we learned about. So any method that works is good. And then for the backward direction, we'll prove that if Q then P, or which you can write like this, this, you just read this as if Q then P, right? It's if Q then P, the arrow is pointing from Q to P. So prove if Q then P using any method. The reason I wrote it this way is to show why we use this backwards arrow. All right, so, well, to show you that it aligns with that. Okay, so we'll do an example of this. So here's a proposition. Suppose A and B are integers. So this is not part of the if and only if. This is just setting it up, right? It's giving you two integers, and it's saying now that we have these two integers, here's the if and only if. A is congruent to B mod 6, if and only if A is congruent to B mod 2 and A is congruent to B mod 3. So we have to prove two things. We have to prove, first of all, we have to prove that if this, then this. And we also have to prove that if this second part, right, then the first part. Okay, so we're going to first do the forward direction. So we're going to start by we're going to use direct proof. Suppose that A is congruent to B mod 6, right? So suppose that this is true, and our goal will be to show that this has to be true. Well, if A is congruent to B mod 6, that means by definition that 6 divides A minus B, which means by the definition of divisibility that A minus B is equal to 6 times n for some integer n. Now we can factor that, right? So A minus B is equal to 2 times 3n, right? 6n is the same as 2 times 3n. So what does that tell us? It tells us that 2 divides A minus B because A minus B equals 2 times an integer, right? This thing in parentheses is an integer. So we have A minus B equals 2 times an integer. So A divides A minus B, which means that A is congruent to B mod 2 by definition of congruence, right? Since 2 divides A minus B, we know that A is congruent to B mod 2. So we're partially done. So we've shown that if A is congruent to B mod 6, then A is congruent to B mod 2, but we also have to show that A is congruent to B mod 3. So let's do that. So also, well, we also know, since we know that A minus 6 is equal to 6n, we also know that A minus B is equal to 3 times 2n, right? We can factor it that way. So now we have that 3 divides A minus B because we have A minus B equals 3 times an integer. So 3 divides A minus B, and thus A is congruent to B mod 3. Therefore, we have both things, right? We have that A is congruent to B mod 2 and A is congruent to B mod 3. Okay, now this was all for the forward direction, right? We showed that if A is congruent to B mod 6, then A is congruent to B mod 2 and A is congruent to B mod 3. Right, so we show that if P, then Q. But now we have to show the backwards direction, right? We have to show that if Q, then P. So let's do the next part of the proof. So we're going to continue the proof. So again, here what we're going to do is we're going to suppose that this part is true. That's what we're going to start with. And then we're going to have to show that this is true. Okay, so we use this backwards arrow to indicate we're now doing the backward direction. Suppose A is congruent to B mod 2 and A is congruent to B mod 3. Well, we're just going to follow the definitions. Well, since we know that A is congruent to B mod 2, we know that 2 divides A minus B, which means that A minus B is equal to 2 times some integer j. Also, since A is congruent to B mod 3, right, we have two things. We're told A is congruent to B mod 2, but we're also told that A is congruent to B mod 3. So since A is congruent to B mod 3, we know that 3 divides A minus B. And so A minus B is equal to 3 times k for some integer k. Notice I'm using different variables, different letters for j and k, because it's not necessarily true that it's not necessarily the same value. Anyways, now what do we know? We know that 2 times j, well, that's even, right? 2 times j has to be even. So that means that A minus B has to be even, right? So we have 2 times j is equal to A minus B. That has to be even. But we also know that A minus B is equal to 3 times k. So that's equal to 3k. So we therefore know that 3k must be even. Again, 2j is obviously even. 2j is obviously even because it's 2 times an integer. We know 2j is equal to A minus B. We also know that A minus B is equal to 3k. So therefore, 2j is equal to 3k. So since 2j is even, 3k must also be even because 3k is equal to 2j. So 3k must be even. Okay, thus k must be even. Why? If 3k must be even, how do we know that k must be even? So here's an explanation. Since if k would be odd, right? Let's say k would be odd. If k would be odd, then what would 3k be? 3k would be 3 times, 2c plus 1, meaning because k is odd. So it would be 3 times 2c plus 1, which would be 6c plus 3, which is 2 times 3c plus 2. I'm sorry, this should actually be a 1. Hold on, it should be a 1. So it would be 2 times 3c plus 1, which would mean that 3k would be odd. But we know that 3k would be odd, but we know that 3k is even. So therefore, k must be even, because if k would be odd, we would end up that 3k is odd. But we know 3k is even. Okay, so k must be even. By the way, what we just did here is kind of like a mini proof by contradiction. But okay, that's fine. Anyways, so let's continue. So we know that k is even. So k is equal to 2m for some integer m. Thus, a minus b, okay, which is equal to 3k, can also be written as 3 times 2m, right? 3 times 2m, because k is 2m, which is 6m. So a minus b equals 6m. Aha, so therefore 6 divides a minus b, because we have a minus b equals 6 times an integer. M is an integer, so we have 6 divides a minus b, and therefore a is congruent to b mod 6. So what have we shown here? We've shown that if we have this, right, if we have q, then we have p. So what have we done? We've proved both directions of the if and only if. So therefore we have proven it, right? Again, the proposition was an p if and only if q. We first proved if p then q, then we proved if q then p, and therefore we have proved the proposition.